Thank you. Good morning, everyone. Thank you for coming. So, like Angel said, I will be talking to you about water hammer. This presentation will be kind of like in two phases. First one, looking at the science, the hydraulics, the numbers behind water hammer, what caused it. And then second part, what are the different solutions to reduce or dampen pressure surges in your piping systems. Just before we start, just want to show a little video to keep everybody awake. Some of you may have seen that already. I need to slide this over. Let me turn the light off here real quick. You want to do that? Okay, thank you. This is a storm sewer in Calgary, Canada. You'll probably see a little bit better when the light is off. But at the middle of the screen here, you have a pretty large manway cover, and it's going to get picked up by the water rushing up the shaft. The reason why I want to show this video is to show the power of water if it's not controlled properly. Pretty big geyser.
That Old Faithful?
It gets better. It gets better. The poor old fellow just run his truck into the manway cover. Can't really see well because the quality of the video is not so good, but it looks like a police car driving by.
You say it's a sewer?
Storm. Yeah, storm drain. The police car just keeps on driving. A few minutes later, the guy's outside checking the damage on his truck. The next thing you know, water pressure comes back. It's shower time. Definitely not a good day for this guy. All right. All right, now that I've everybody awake, let's get into the boring stuff. So pressure surges. What causes pressure surges is when you have a closed pipe with no air in it. It's just complete fluid, pressurized, and you change the velocity of the fluid. You have that water or fluid moving down the pipe at 2, 3, 4, 5, 10 feet per second. And you either slow it down or accelerate it by closing a valve, turning off a pump, and then when you do that, the pressure changes because of the change in velocity. And the magnitude of the pressure change based on how quickly you stop that water column. The worst case scenario very often is when you have a power failure. You're pumping full flow, you have a power failure, and all your surge protection devices, or say pump control valves, the VFDs and all that, cannot control the rate at which the water column slows down. So you get a serious pressure surges and sometimes water hammer. So what happens when the pump stops? You can compare a locomotive pushing a set of carts down a railroad track. This locomotive is moving at 60, 70, 80 miles an hour. And picture a gigantic hand just grabbing the locomotive right there and stopping out on the tracks. Well, the carts have accumulated a certain amount of kinetic energy. So they will keep on moving down the track, and then under the effect of gravity, come back down the hill and slam on the locomotive and create a high pressure. Well, it's essentially the same thing with a pump pushing the water down the pipe. That water column is your carts, but the water is moving at 4, 5, 6 feet per second. And as soon as the pump stops, the water column will keep moving down, and then eventually come back and slam down on your check valve and create a high pressure surge. When you have a valve shutting off, it's the same thing. You have that water column coming crashing on your valve, shutting down. So the faster you shut that valve off, the higher the pressure surge will be. So when you have take the example of a valve in the middle of a pipe. You have, let's say, 5 miles of pipe, 10 miles of pipe, and right in the middle, right in the middle you have a valve, and you close this valve in 5-10 seconds. If you have a pressure gauge on either side of your valve, what you will see is on the upstream pressure gauge, the pressure will spike up, and on your pressure gauge after the valve, that pressure will drop down really rapidly. And depending on how quickly you close the valve and how fast the water is moving down the pipe, the pressure downstream of your valve could possibly drop to full vacuum. And when that pressure drops to full vacuum, you get water column separation. And when that water column separates, you have the formation of a big vapor pocket, cavitation inside the pipe. And when that vapor pocket collapses, this is when you get high pressure spikes and you hear the typical sound of water hammer, like somebody's hammering on the pipe. Here's a little example showing that. So you have your pump on the bottom right corner. You're pumping up to elevated storage tank, and the pump stops. You have a power failure. What happens is that water column stretches. You have the formation of a vapor cavity. That vapor cavity expands, it grows, and then eventually the pressure wave comes back and collapses this vapor pocket. And when it collapses, you'll get your boom, your pressure spike sound effect. Pretty fancy. All right, so here you'll see in the video what the water column separation looks like in the pipe. So when the clock hits about 40 seconds, you'll have a pump stop. So we have a pump on the right side of the screen pushing water from the right to the left. A section of this check valve has been replaced with a transparent pipe, so you can see inside the pipe what's going on. And as soon as the time hits 40 seconds, you'll hear the pump stop and the water column separating in the pipe. So the pressure drops to a full vacuum, negative 14.7 psi at sea level. But here's another video, same deal. On the right side of the screen, you have a pump pushing the water, and it's moving from the right side to the left side. A couple of pieces of pipe have been replaced with transparent pipe, so you can see the inside of the pipe. And this one is more dramatic, I'll say, because you hear the water hammer a lot more. You see it goes back and forth in waves. It's not just a one-time deal where the water column separates and then gets back together. You have pressure waves going back and forth in the system. Here's another one showing the same thing but in slow motion. So the pipe is full of water. You can see at the top right corner the time in seconds. It's a really fast phenomenon. So the pump stops, water separates, you have the formation of a vapor pocket. In this experiment here, the vapor pocket is not very big, probably a couple of feet long. But in some instances, when you have a very large diameter pipe, large flow, this vapor pocket can expand to several hundred feet. And the larger, the bigger the vapor pocket is, the more damage it will do when it collapses. It's like two freight trains just hitting each other dead on. So the reason why I'm showing this videos of water column separation is because many people oversee this aspect of pressure surges. They only worry about the high pressures exceeding the pressure rating of the pipe. So they try to install devices to relieve the high pressure, like surge relief valves and things of that nature. But if you can give energy to the system to prevent the water column separation from happening in the first place, then you will not have high pressure surges when that water column gets back together or when the vapor pocket collapses. So if you were to install a pressure recorder downstream of a pump and look at the pressure recordings following a pump trip, you could gather something like this. here for this specific system, the pump is pushing about 45 psi. And then about 5 seconds into the simulation, you have a pump trip. The pressure drops to a full vacuum. So this flat line here at the bottom is not an error. It's the minimum pressure, negative 14.7 psi. Pressure cannot physically drop below this. It's a full vacuum. So the water column separates, the vapor pocket grows, and then eventually, after 10 seconds, collapses. You get a pressure spike up to 250 psi. So it's a really low pressure system. You wouldn't imagine that you can get pressure spikes up to 250, close to 300 psi, but it is possible if you...
What is the pressure in the system?
Here, in this case, pumping pressure when the pump is running about 45 psi.
Okay.
Oops. Just a few pictures of things blown up. So you have two types of cavitation. Most of you guys are probably familiar with cavitation, dynamic cavitation on a pump impeller. Is when you're close to a pump and you hear it cavitate, it sounds like there's a bunch of marbles in it or rocks. And it's because the pump, I guess the net positive suction head is too low. So the pump is lifting water from a source that's way too low, like 30 feet lower. And the weight of the water column creates negative pressure, full vacuum inside the pump. So you can see in this picture here, it's the inside of a pump impeller, inside of a pump. And right on the edge of the blades of the pump, you have small bubbles. And those small bubbles, it's actually the water separating because the pressure drops to a full vacuum there. And once those little bubbles collapse, it eventually erodes the pump impeller over time. And you end up with an impeller that looks like this. And it has to be, the pump loses its efficiency and so on, and you have to replace it over time. So if you have, if your small little pockets, like you saw on the previous picture, can destroy your pump impellers, much larger pockets, vapor pockets, hundreds of feet long, can definitely blow your pipe out of the ground. So here's an interesting video. It's actually a video about a shrimp. I'm sure you guys didn't expect to see this kind of video this morning, but you'll understand why.
Hiding under the rock is a pistol shrimp, and he's packing a lethal weapon. This crab is heading into trouble. Our shrimp is ready for a fight. At first sight, it looks like he's punching the intruder with his claw. But in fact, something much stranger is going on. Something we can only see if we look again in slow motion. That sound we hear is not from the claw itself, but from an amazing invisible force. The claw snap happens so fast, it causes a high-velocity water jet which shoots forward at almost 60 miles an hour, fast enough to vaporize the water and form a bubble. But this is no ordinary bubble. For an instant, it's as hot as the surface of the sun, and as it collapses, this vast energy is released like a superheated shockwave, stunning or even killing its prey. The knockout punch comes not from the claw, but from the super hot power of a bubble.
Music is very dramatic. I was watching National Geographic one day and saw this video and thought it would be a good addition to this presentation. So this little bubble that you saw in the video, when it collapses, it releases a lot of energy. You can see a couple of pictures here of a surface of a pipe which was exposed to a vapor pocket collapsing and then created a small indentation. And then if this happens over time, several times over the span of a day, a week, or a year, over time the thickness of the pipe decreases because of erosion. the vapor pockets inside the pipe start eating the surface of the pipe, and eventually your pipe, which could be rated for 160 psi, then after 3 years, 4 years, 5 years of service, it's probably only good for 100 psi or 90 psi. So controlling the negative pressures or preventing negative pressures from happening inside the pipe is very important for that reason. Here's another one. And I'll open this one differently because it's a long video. I need to skip through it. Here it is. Now, I don't speak German. I don't know what they're saying. All I know is this is a test that was done in Germany back in 2000. And this is a very high pressure rated pipe. And what they're doing is they are pumping water through the system very fast. The water is moving at 30 feet per second, so it's really, really high. And they're going to close a valve, a solenoid activated valve, really fast, almost instantly stopping the water in the pipe. And they've installed pressure transducers, recording pressures 100 times a second, different points in the system, just to analyze what water hammer looks like in the field and how pressure waves propagates and stuff. But the reason why I want to show this video is because the sound here is really impressive. So here's your valve. The water now is moving down the pipe. The valve will just close one time, and then you'll hear pressure waves moving back and forth, but the valve only closes one time. There it goes. That's the same system. It just recorded videos at different areas, at elbows and junctions and T's, and there you go. So you can see the heavy-duty flanges and how the pipe is restrained. It's made to take the abuse, but your typical pipe in the system is not rated for this kind of abuse. Now, with certain types of pipes, pressure doesn't necessarily have to drop to a full vacuum. If you have a concrete line pipe, for instance, if the pressure repeatedly drops to, let's say, -5, -10 psi every time your pump stops and pump starts, then over time what happens is the layers inside the pipe, the concrete lining, starts to delaminate. It comes apart and eventually it collapses in the pipe. So you end up with something that looks like this. And the metal under the concrete lining becomes exposed to the water and the gas and so on, and you get corrosion issues. It's not something you necessarily have to worry about with PVC pipe, but with those types of pipes, even partial vacuum is an issue. Oh, sorry. Yeah. Here's another example, very large diameter line, 1200 millimeter diameter. That's, I don't know, 60 inch probably. And you'll see the pipe moving under the effect of a vacuum. It will just, looks like it's breathing. So this system, it's in Brazil, had several line breaks. It's a penstock going down to a dam. And every time the valves would open and close, it would cause an issue at the high point where pressure would drop to a vacuum. Now, I don't know about you, but I wouldn't be standing there recording. I'd be running as fast as I can.
What kind of pipe is that?
It's steel pipe. Another one in France. We have some fine engineers over there too. This discharge header might need an air valve. I like this picture because it's a potable water pipe that kept on breaking at the same point, at a high point. And instead of looking for a solution to prevent the breaks from happening, this section of pipe just kept on getting replaced over and over and over again. And so during the repair, one day, there was a temporary bypass pipe that was just laid on top of the ground just to bypass the break while the repair was getting done. And then they had a power failure, so the temporary pipe that was laid on the ground during the repair just collapsed on itself. So you ended up with this picture. Pictures of various pipes collapsing. And so the one on the left side here was a picture of a PVC pipe. It's in Georgia. It's irrigation water for a golf course. And they had the same issue, pipe breaking at the same point over and over and over again. So after a while, they decided to look for the actual cause of the issue, the cause of the pipe breaks. So we run a surge analysis on this system, and then ended up sizing a small surge tank. The surge tank was placed at the pump station right next to the pumps, and never had an issue ever since. So all these videos, you saw the pipe breathing. You have pressure waves going back and forth in the pipe. And those pressure waves, the velocity of the pressure wave depends on the pipe material, diameter, the type of fluid, the thickness of the pipe. And a general rule is the stiffer the pipe is, like a ductile iron or PVC, a ductile iron or steel pipe, you'll have pressure waves going up to 4,500 feet per second, 5,000 feet per second. Whereas your PVC pipe, HDPE pipe, something more flexible, the pressure waves will move somewhere in a 600 feet to 1,800 feet per second range. Now, what I mean by pressure wave is, I want to show a little animation here. You'll understand what those look like. All right, so let me explain what we have here. We have a pump on the bottom left corner, moving water up to either a manhole or elevated storage tank. And the green line over here is your hydraulic gradient, HGL, or a hydraulic grade line. And it shows the pressure at every point in the system. The higher the distance between the center line of your pipe and that green line, the higher the pressure. So here at the pump station, for example, you have, can't see really well, but it's 88 PSI. And here at this high point, the distance is lesser, so you have 35 PSI and so on. So what I'll do is run this video. It's an animation of what the pressure looks like in a pipe following a power failure. And what you will see is that green line moving up and down. And you'll see the pressure waves going back and forth in the system. The higher, obviously, the higher the pressure, the green line goes, the higher the pressure. The lower it goes, the lower the pressure. And if that green line goes below the pipe, it means the pressure in the pipe is negative at this point. And you'll see water column separation everywhere where the water inside the pipe turns black. So here we go. Pressure wave is moving away from the pump station following a power failure. And over here you get negative pressures. And it falls to drops to a full vacuum. So you have water column separation happening about 5,000 feet downstream of your pump station. So ideally what you would want to do is maybe put a vacuum breaker or a combination air valve at the high point to prevent the vacuum from happening inside the pipe.
Do you run an animation where you show that on there?
What do you mean?
Do you run an animation where you show the
Yep.
vacuum breaker?
Yep.
that's mitigating?
Yeah, so I'll run the same scenario with an air valve, and then I'll add a surge relief valve, and then add a surge tank. So you can see how each device provides different degree of surge protection. Oops.
What kind of pipe material did you assume on that?
This, if I remember correctly, I think it was a PVC or HDPE pipe. It was a low wave speed, about 1,800 feet per second. So what are different ways to reduce water hammer? Well, flywheels, combination air valves, VFDs, pump control valves, surge relief valves. There's different ways to do it, and we'll go over each one of those. First of all, flywheel. The idea behind a flywheel is to add some mass, some rotating inertia to your pump. So when you have a power failure, this flywheel will keep the pump spinning for a pretty long period of time, 2 minutes, 3 minutes, 5 minutes, 10 minutes. So the pump keeps pushing water down the pipe. And instead of having your water column going from 5, 10 feet per second to a 0 over the span of 2 or 3 seconds, it slows down over the span of 60 seconds or 2 minutes, so you don't have the quick pressure drops. The main disadvantage is it's huge. It requires a lot of extra power or electricity to put this wheel in motion from the pump. And if it's not calibrated correctly, you can create a lot of stress, a lot of vibrations that will eventually damage your pump and your motor. Vacuum breakers. So those have to be installed. So those are typically installed at high points. When you have a pipe going along, we don't have many of those here, but hills and mountains and things like that, you typically put them at every high point. And we'll see that, I'll go back to the animation, but we'll see that having those vacuum breakers at every high point may not be enough. You may have to install some at unusual locations, like along slopes and so on, in order to prevent vacuum. Main disadvantage of vacuum breakers is, especially on sewage, they tend to clog very rapidly, require a lot of maintenance, and also they can be an odor issue. If you have one installed somewhere in a neighborhood where you have lots of houses and so on, every time the pump stops, the vacuum breaker will introduce a lot of air inside the pipe. And then eventually when the pump restarts, then all the air, the foul-smelling air will come out of the pipe and create a nuisance for people around. Surge anticipation valves or surge relief valves, there's different types. Those devices work great, but they only take care of half of the water hammer issue. What I mean by taking care of half is they only release high pressure. They don't do anything to give energy to the system to prevent water column separation from happening in the first place. So in order to use those devices, you would have to use a surge relief valve in combination with air valve strategically placed along your pipeline. So the air valves take care of the low pressure problem, and your surge relief valve take care of the high pressure problem. VFDs, and I'll put VFDs and pump control valves in the same category. Those slowly ramp up the pumps and slow down the pump, or slowly open and close to control the flow rate when you turn the pump on and turn the pump off. They work great during normal operations, but if you have a power failure, they won't do anything to control the rate at which you turn the flow on and slow the flow down. Sorry. Standpipes. A standpipe is just like a big source of energy right next to your pumps. Let's say you have your pump right next to the standpipe, and you're pumping along a very long pipe. When you have a power failure, you have this source of energy. The water is, you have, 100 feet of water inside the pipe. So when the pump stops, what will happen is the water inside the pipe will start going down and fill the void that would be left in the pipe and prevent the water column separation, so give energy to the system. And when that water column comes back, the standpipe will start filling back up. It works. It's a great solution. The main disadvantage is they're tall. They have to be as tall as what your pump output pressure is. So if your pump is pushing 150 feet of of head, then your standpipe will have to be at least 150 feet because it's open to atmosphere at the top. The main disadvantage, they're tall, expensive, ugly. Really, nobody wants to have one of those in their backyard. A bypass with a check valve. So you have your pump, and you put a bypass around it with a check valve. And what that does is when you have a power failure, you use your upstream pressure to give energy downstream to prevent water column separation from happening over here. That only works in the case of a booster station. Let's say you have 50 psi upstream and 200 psi downstream. When your power fails, the pressure downstream will start dropping up until it gets to about 50 psi, at which point the bypass opens up and you maintain your downstream pressure using the 50 psi upstream. Now with this system, you have to have upstream pressure. You cannot use this method if you have like a lift station or something with zero pressure on your pump suction. And then a surge tank. Surge tank, what it does is it works the same way as a standpipe. So it gives energy and receives energy. And the difference is it's close to atmosphere. So if your pump discharge pressure is on 100 psi, you won't have to have a standpipe that's 230 feet tall, really. But the surge tank is close to atmosphere, so it's much more compact solution. So now I'm going to go back to the animations and show how those devices will provide or dampen water hammer. All right, so here what I have is I have a surge relief valve at the pump station and an air valve placed at the high point over here. So this is what you would typically have, just the air valve at the high point. So your surge relief valve takes care of the high pressure, and your air valve takes care of the low pressure, or supposed to. So the pump stops, pressure drops, pressure wave goes down the pipe. It's intercepted by the air valve at the high point. But if you go back here, I'll pause. So the pressure wave is moving down. And as soon as the pressure drops to 0 psi over here at the air valve, it opens up and starts introducing air in the pipe, controlling the vacuum at that location. But if you continue the simulation another few seconds, you'll see over here, you have about 1,500 feet of pipe subject to a full vacuum. So in order to control vacuum for this system, you would have to have another air valve here, maybe another one here, because otherwise you still end up with a full vacuum in the pipe. So it's not, that's what I said earlier by not common location or not a typical place for an air valve. Usually they're always placed at high points. But here to control vacuum, you have to run a surge analysis and place one here and one there. So that's what we'll do next, run the next simulation. All right, so I have another 2 air valves, one here and one there, and you'll see the difference now. You still get some vacuum, some full vacuum over here, but it's just for, it's a blip. It really won't won't cause any serious damage. So now this system is pretty effectively protected with 1 surge relief valve and then 3 air valves along the pipe. So here's your animation with the surge tank at the pump station. So the surge tank is giving energy, effectively controlling the rate at which the pressure drops. And positive pressure is maintained everywhere throughout the pipe.
Gwenn,
Yeah.
so what's your discharge condition on the right-hand side? What are you discharging into?
This could be a manway. It's just open to atmosphere. So for this example, it's wastewater. So you're discharging into a manhole at a high point. So really not much going on with a surge tank.
Could you suggest that a surge tank would eliminate all the air valves?
Yep. Yeah, this was just a surge tank, no surge relief valve, no air valves.
Because operational staff would love that.
Yep.
They just have to.
A lot less maintenance, I would imagine.
Yeah.
We still have to have our valves at the high points.
Still have to have air valves.
Still have to have air release valves at high points because otherwise air would end up trapped and restricting the flow if you didn't have a surge tank. If you didn't have air valves. In order to do a surge analysis on the system, it's fairly simple. There's different types of surge analysis software on the market, Bentley Hammer, KY Pipe, there's different names on the market. And it can be done really easily if you have a complicated water distribution system, for example, and you have a WaterCAD file. This can be directly imported into a surge analysis software. You run your calculations, and you can see which areas in the system are problematic. If you don't have anything like this, if you're just dealing with a simple pumping from point A to point B, like a sewer force main, a model can be done fairly easily. Just using the profile of the pipe, pump curves, drawings of the pump station, and then you can run different scenarios and see where you have to place your air valves or surge tank and what size and whatnot. Here's a picture of a fairly decent sized water distribution system where they had customers on top of a hill which daily would experience complete loss of water pressure for a few seconds. Then it would come back, and then it would it would go away again. And every time they had one pump station which didn't have VFDs and things like this, so every time the pump stopped, it would throw those negative pressure waves in the system. So eventually, by running a surge analysis, they found out which pump station was problematic, added a surge tank to this pump station, and the pressure at the high point was maintained. If you were to look at a comparative graph of pressures, going back to one of the first few slides, where we had the pump pushing 45 psi, dropping to full vacuum, and going back and forth, you can see with a surge tank the smoothness of the pressure trace. So there's different types of surge tanks. What I'm going to go into now is surge tanks, how they work, and different types. You have compressor-style tanks and bladder tanks. Your compressor-style tanks, reason why you have to have a compressor is because you have your water and then a pocket of compressed air on top of it. And what happens over time is your compressed air will dissolve in the liquid. So your water level will start rising up and up and up, and then eventually your tank will be full of water with no air, so pretty much useless. So you have to have a control panel with a level monitoring system, a compressor, which on a daily basis or several times a day will kick on and add air back in the system to bring the water level back down. With a bladder tank, you have a rubber membrane inside the tank that provides a barrier between the liquid and the gas. So you have no air dissolution over time. So you eliminate the need for the control panel, the air compressor. You have no power requirements, no external life support system needed with the bladder tank. It's a much easier solution with less maintenance. There's different types of bladder tanks for potable water, for sewage, for petrochemical applications. For potable water applications, for example, we like to put the water inside the bag, or put the water inside the bladder. So this way you have no contact between the water and the walls of the surge tank, so no risk for corrosion. And over time, for a compressor tank, for example, the inside of the tank would have to be recoated every 10 to 15 years. Requires a lot of time to do that and a lot of money. But with a bladder tank, granted you have to replace the bladder every 10 to 15 years, but you have no risk for corrosion. So the lifetime of the life cycle of the tank will greatly outlast your life cycle of the pump station. At the bottom of the tank, you can't see it well here, but there's an anti-extrusion grid which prevents the bladder from getting sucked in the pipe in case you were to lose your line pressure. Charlotte, we can manufacture those bladder tanks up to about 40,000 gallons in horizontal configuration. and up to about 18,000 gallons in vertical configuration. The bladder is for a vertical tank. It's attached both to the top of the tank and the bottom of the tank. So instead of having the bladder just lifting up and down and creating a lot of stress on it, it opens and closes this way, creating much less stress on it. For horizontal tank, it's attached to the bottom, and the bladder is the exact same size as the tank itself. So if you have a 5,000 gallon tank, you'll have a 5,000 gallon bladder, because if the bladder is smaller than the tank itself, when it expands all the way, if it expands all the way, then it would create a lot of stress on it and could cause some premature rupture. On the wastewater, it's the opposite. The tank is only vertical. Can't put a horizontal tank on wastewater because of sedimentation concerns. And the bladder is hung from the top of the tank. So your compressed air goes inside the bladder and the sewage is outside of it. Same thing, there's an anti-extrusion grate at the bottom of the tank to keep the bladder from getting sucked in the pipe and also keep large debris from entering the tank. And the bladder is made of, for sewage, is made of butyl rubber, but it's 2 layers of butyl rubber vulcanized together. And in between the 2 layers, there's like a Kevlar-like fabric vulcanized between the two, so sharp objects that would puncture would go through the first layer, but would be stopped at the intermediate fabric material. And there's another type of surge tank called a dipping tube tank. So this tank doesn't have a bladder and doesn't require a compressor either. And this is for very specific applications, mainly on sewage or raw water, where you have a very long and flat force main, and every time you turn your pumps off, the pressure drops to a full vacuum. So you have, not full vacuum, to atmospheric pressure. So you have very low static pressure. You're only pumping up to, I don't know, probably 5-10 feet in elevation difference. So what that does is, whenever the pump starts, the water goes up inside the tank, up to the bottom of the tube, and fills up, and you have a float at the top of the tank. So all the air goes out to the float, and eventually when the sewage gets up to the top of the tube, it closes the float, and you end up with a pocket of compressed air outside of the tube. And what this compressed air does, it provides elasticity, provides energy to the system. It does the pressure dampening effect. So when you have a power failure, the tube opens up, the vapor pocket, the gas pocket expands and just gives energy to the system, controls the downsurge and the upsurge in the system. So with this one, you have no requirement for bladder, no requirement for a compressor, and virtually no maintenance except for cleaning the float at the top of the tank every 3 or 4 months. A few pictures of the manufacturing facility. Didn't mention, but Charlotte is a French company. So the factory is located about an hour and a half, 2 hours south of Paris. And we also have a contract with a US company called Steel Fab. They're located in Virginia. They make part of their production. All the tanks are ASME certified. Everything for potable water is NSF 61 certified. All the welds on the tanks are robotic welds inside and outside to ensure best quality. Now there's the way we make the tanks is, especially for bladder tanks, the way the end caps and the shell are made together. There's an easy process for manufacturing, which is called, it's lap welding. So the end of the tank, or the end of the end cap, is put inside of the shell, and then only the outside is welded. But this causes a lot of issues with rust on the inside, or even if the outside and inside are welded, pressure differences over time, and then thermal expansion creates a lot of stress on the weld, and then eventually on the inside of the tank you have cracks on the paint and moisture gets underneath the paint, and you end up with something that could look like this. So, and also the other issue with that is with lap welding on the bladder tank, you create a lot of rough spots inside the tank and angles and things that would put a lot of stress on the bladder when it inflates and deflates. So by doing another process, by doing a butt weld instead, then you eliminate these issues. It's a more expensive process, but By doing this, we ensure that on potable water, the lifespan of the bladder typically is anywhere from 15 to 20 years, and on wastewater, you're looking at 10 to 12 years. So we make our own bladders. Everything is made at the same factory. So the bladders are made and tested at the factory, make sure there's no leaks before they are inserted inside the tank. We do our own painting. Everything is done at the same plant for better quality control. The tanks are pressure tested at 1.5 times their design pressure. So if you have a tank rated for 100 psi, it will be tested per ASME procedure at 150 psi, just to make sure there's no failure points anywhere on the tank. Now, one question with bladder tanks often is, how do I know if I have a rupture on the bladder? Well, what will happen over time is if you have a rupture, you have contact between the air and the water. So your compressed air will start dissolving in the water, and then over time, your liquid level will start going up and up and up. So you have two ways. You can install a magnetic level gauge or a liquid level transmitter, or differential pressure transmitter, and you have your high and low level alarm set on it. So if you have a rupture in the bladder, you will trigger your high level alarm. The operators will be notified that they have to come and perform maintenance on the tank because something is wrong. Here's a picture of the interior of a horizontal potable water tank. This one has two outlets, one here, and the next slide shows the clamping system for the bladder to be attached to the tank. It's pretty heavy duty, and this is an anti-extrusion grade for potable water to keep the bladder inside the tank. Here's a picture of the paint booth. We do our own sandblasting, cleaning, own painting, and we have a pretty large oven too that cures the paint on the tank. Typically, we use 16 mils of epoxy paint on the inside of the tank, but any kind of paint can be specified. A few pictures of installations. Tanks can be made in all shapes and sizes and colors. Insulation for cold environments, whether it's a bladder tank or compressor tank, we recommend installing insulation jacketing on the outside of the tank to prevent freezing. Just pictures of a few installations. Next one is a pretty large installation. We have four 25,000-gallon bladder tanks installed in Toronto. And the reason why I like this reference is because this pump station was originally commissioned in the late 1970s. And it's a large diameter pipe. It's about 11-foot diameter pipe, conveying potable water from the water treatment plant up to an elevated storage tank. And this existing line is protected by compressor tanks. There's two 50,000-gallon compressor tanks. And about 10, 15 years ago, phase 2 of the project was started, where the second line, same diameter, same flow rate, was installed right next to the existing line. And the city of Toronto requested to have bladder tanks installed to protect the pipe instead of compressor tanks to reduce the maintenance. They had so many issues with the compressor and with the existing tanks where they had to recoat the interior and rust and things of that nature. So they installed bladder tanks instead and reduced their maintenance cost tremendously. Here's a picture of a tank installed in Chicago. This one is about 30,000 gallons, and you have a picture of the bladder that goes inside it. It's a pretty big piece of rubber.
How long is that, and how do you ship it?
This tank is 16 meters long, so that would be about 45 feet long, I believe. And the tank is installed, everything is put together before shipping. So once the tank arrives on site, it has to be unloaded with a crane. And during commissioning, what you have to do is just connect the compressor to the top of the tank, pre-charge the tank with what we call the pre-charge pressure. So that pre-charge pressure is based on the surge analysis, whether it's 20 psi, 40 psi, 60 psi. So bring a compressor on site, commission the tank, and then once the tank is pre-charged, you can open the isolation valve, let water fill the bladder, and the tank is in service at that point, pretty much. It's really easy device. So yeah, I mean, those are pretty big piece of equipment. One of the main downside of surge tanks compared to like surge relief valves and air valves and so on is in some instances they can require a pretty large footprint. And in cold areas, you might have to have a building around them and so on. So it's a larger initial investment, but then over time you save money on maintenance and things like that. Just a few more pictures of installations all over the place. We have surge tanks on all the continents, probably not North Pole and South Pole, but there's one not far from us, Omaha. And I think that wraps it up. Anyone have any questions? Yeah.
Talk about the life of a bladder.
Mm-hmm.
We have the two options, water-filled, air-filled.
Correct.
Is there a difference in terms of expectation on the bladder life with if the water is used or the air is used?
Well, life expectancy of the bladder depends on different factors. One, like you said, if the water is inside the bladder or if the bladder is hung from the top. Typically, we'll use those vertical tanks with the bladder hung from the top on wastewater and raw water applications, so it's more aggressive. So the life expectancy of the bladder would be, for those applications, 10 to 12 years. Now, on a horizontal tank with the water inside the bladder, those tanks they're potable water mainly, so the life expectancy would be 15 to 20 years. Another thing to take into consideration is the life expectancy of the bladder depends on the number of cycles. On the lift station, for example, you have your pump starts and pump stops. You probably have 4, 5, 6, 7 per hour, where on a potable water system, very often your pumps are on VFD, so the pressure fluctuations are very minimal. So on a potable water system, the bladder will last a lot longer than on your sewer applications. And I think that's all I have for today.